Okay, this is a talk about mitigating side channels. Okay, so I'm going to take you all on a journey of getting rid of side channels once and for all in this talk. Okay. Wait, that was not the funny part. Okay, so are you ready? Who wants to solve this whole thing in the next half hour? Great, great, great. Let's do it. Okay. So, DramaQueen. This is about revisiting side channels in DRAM. Okay. Oh, yeah. We're going to save the world after this slide. This slide is something that corporate lawyers make me put up sometimes. They say, Ben's opinions are not my opinions, and well, vice versa. Their opinions are not my opinions. So, I'm not speaking for them, basically. Okay, so this is the topic of this talk is about classical side channels. Classical side channels means it's kind of before, roughly speaking, before the meltdown era. Classical side channels are a method of spying on the activity of a victim because the activity of the victim gives away some secrets. It means that the victim is doing some kind of data-dependent activity, secret-dependent activity. An example is in this code. This is a point scalar multiplication of some crypto code, some elliptic curve code, and the danger is this if statement. So the scalar is the secret. We loop over the bits in the scalar and do this add only if the bit in the scalar is on. That is secret-dependent activity, because we only do this add when the bit is on. If the bit is off, we do not do the add. So that's the secret-dependent access pattern. And it is the opinion of many hardware vendors, generally speaking, that this is a software problem. This is, well, okay, it's because they're different, based on the secret, there's different activity in the caches, and a spy who's accessing the caches can deduce this pattern and figure out the key. And generally speaking, CPU vendors and so on, generally speaking, say, that's the software's fault, figure it out. You have to write your algorithms in a constant time kind of way. You have to, no matter what the secret data is, all the instructions have to be the same, the timing has to be the same, cache access patterns have to be the same, TLB access patterns have to be the same, microarchitectural changes have to be the same. Just don't let it depend on data, and then it's secure. Okay, no more classical side channels. But maybe we don't. Maybe that's hard. Maybe we just want to use an insecure implementation sometimes. Maybe we want defense in depth. Maybe a constant time algorithm one day is not constant time anymore when a new compiler version comes along with a clever optimization, or a new microarchitectural feature comes along, or a new exploit comes along, like memjam. That's an example from the past. There are crypto implementations which assume that visibility of an attacker is up to a cache line, which is a reasonable assumption. But when memjam came along, the granularity suddenly got better, and then previously secure implementations were suddenly not secure anymore, based on visibility of this kind of access pattern. So, this talk is about, can we just make this insecure code secure by making some compromises? Okay. However, well, it's going to be a strawman cache attack immunity framework. Okay, it's not going to work. We're going to take a solution that seems like it would solve all problems, and then we're going to show why this solution is not complete because of a DRAM side channel. So we're going to talk about what is this supposed solution to all problems. Then we're going to talk about, okay, but can we observe activity outside the CPU in DRAM? And then we're going to exploit that to break our perfect solution. So it's kind of a cautionary tale. Maybe you work for a CPU vendor that, and someone has the good idea that says, hey, can we just implement a save feature, like safe mode, you know, like Windows 95 had a safe mode? Can we put the CPU in safe mode for a couple of instructions while we execute this crypto code, turn off the caches, turn off this, turn off that, then turn it back on again, and at least we know no more security problems. Well, I'm here to say, if you do that, don't forget about DRAM and maybe other things. Okay, so can we forget about classical side channels, okay? So here's an idea. Security critical code, like the code we just saw, right? This point scalar multiplication in elliptic curve code. Can we just turn off, while we're executing that, we're going to turn off the caches. Okay, not turn off literally, but bypass them. Our code is not going to use them, so we're going to map the code uncached. So the page stub is going to say, don't use the cache for this code. The data that it accesses also uncached. We disable for the time that the code is executing, we disable hyperthreading, so there's no concurrent access to microarchitectural state from a sibling hyperthread. So you might think, okay, cache attacks are impossible. Microarchitectural buffer probing is impossible. Okay, no more side channels, right? So to do this, we can use this framework, which already exists, Context Light, which was built by the Gras team, which is a solution to a different problem. It's a solution to mitigate Spectre, but for different reasons than it works for Spectre, it also would work against implementing this idea, which is turn off caches while for the time that you were executing this security sensitive code. So if we use this framework, it means you can annotate some functions and some data. We're saying this handles security sensitive information, then the code in those functions will be put together in linker script in pages which will then be marked as uncached or made uncached at runtime, and ditto with the data. That mitigates Spectre, because during speculative execution you cannot access uncached mapped pages, and also mitigate problems that we're talking about because we're not making any access to caches, so you also can't exploit cache attacks if we're not using any caches. Okay, so disabling SMT as well. So is the problem solved now? Okay, here's a little detour. I'll keep this short because you've probably seen explanation about this many times today. So let's go over how DRAM is accessed. As many people have already said today, DRAM is organized by rows. All the bits are in rows, and what is in the row is capacitors. Every capacitor stores a bit. How does the memory controller access DRAM data? It does so by sending an activate command. This activate command says, hello, can I please get some data from this row? The row is copied to the row buffer. As Michele said, that's a destructive read. The charge is sucked out of the capacitors, copied into the row buffer. And then when the controller that says, okay, now I want bytes, please, then it says, okay, read this or that column, and the bytes get sent over the bus. And then we have to put the row back again, and charge the capacitor back up again, so the data is kept again, and the read is complete. Now this takes time. That's a total pain if you want to access multiple rows in sequence in the same bank, because you have to serialize on this row buffer access. Because of that, the system will try to use multiple banks so that accesses are interleaved as much as possible over different banks. So you can see here, if we access this bank in parallel with that bank, it's fast because there's no conflict. We can use that row buffer here and that row buffer here. But if you access these two rows at the same time, it's slow because one has to wait for the other. So here you can see, as a further illustration, if you're accessing the same bank in different rows, you have to activate row X, read row X, and pre-charge the bank again. And after that, you have to activate row Y, read row Y, and then pre-charge the bank again. One has to wait for the other. If you access different rows in different banks, then you can do two at the same time. And that is why, and the reason that we can, that this is interesting to a security person is, okay, my read gets slowed down sometimes it's not. That means I have, if I'm reading something in a row all the time and I suddenly see a latency spike, someone else is accessing the bank. Someone else is accessing a row in the same bank that I'm present in. I'm the attacker. Interesting. Okay, so here's an image of how that looks. On the x-axis we have physical memory address. On the y-axis we have the same physical memory addresses. And the color indicates what is the latency when I access this pair of addresses. So So most of the time is sort of here in the middle, but there are some peaks here. These little square peaks mean that somehow a delay was incurred. So that means that when I access one address and I suddenly see a little peak, a little yellow color, that means that someone else, if I didn't do it, someone else must have been accessing one of these other addresses. So I can detect this access. On the diagonal, that's also interesting, but a different phenomenon. That's probably, because we can't look into the hardware, so we don't know. But on the diagonal, there's this fast access, which probably means that the two addresses were mapped into the same row buffer. So they're in the same row, so the row buffer accessing, the two addresses go to the same row. You can both access them from the row buffer. So in the diagonal, there's probably no switching going on, so it's extra fast. So that means if I'm an attacker and I can see this kind of this latency, because all these accesses are uncached, right? They go straight into DRAM. If I can look at my DRAM accesses and I'm observing a victim who's using this supposed cache attack immunity framework, which solves all side channel problems because we're not sharing any resources in the CPU anymore, then I can observe the accesses that the victim is doing because I'm looking at what accesses are appearing into DRAM. I'm looking at the DRAM all the time. This victim who is hiding away into DRAM from the cache is suddenly completely naked. But okay, let's see if we can exploit this. Because just like CPU caches, DRAM is a shared resource, and an attacker can monitor this access time. So if the victim goes and does these secret-dependent accesses again, then we can detect, even though, let's say we want to detect whether this add point is happening, because that means that we can distinguish 0 bits from 1 bits in the scalar. If I, as an attacker, am accessing a particular address in a row in a DRAM bank all the time, and I suddenly see a little spike, that means that some activity has happened, and even if it's not bit specific, then that little spike will be delayed by this add point happening or not. So if I see a very regular pattern in the spikes, then I can see that the victim is executing the loop, and suddenly I see a delay in the spikes, then I can tell, okay, I think I've seen an add point happening. So I can start to try to guess, is this a 0 bit or a 1 bit in the scalar? And if I can just observe this a couple of times while practicing, and then observe it while knowing the ground truth, and then I observe it again without knowing the ground truth, I can probably make a very good guess what the key is by comparing my practice run to the real run. So let's see if we can exploit this. We apply the perfect universal solution to all side channels, this cache attack immunity framework. That means that all code accesses go straight to DRAM, not into the cache. All data accesses go straight to DRAM, not into the cache. Cache attacks are impossible. The attacker then monitors a single address that is somewhere in the same DRAM bank as some other address that the victim is using. And then we make the victim start this crypto operation. And first we let it execute a couple of times while knowing the ground truth. Right? We want to know, is the bit a 0 or a 1 that it's processing? And then we can kind of see, do we see a difference in the latency signal between a 0 bit and a 1 bit? And we can visualize that in this way. Okay, so if you remember, we can do a duplicate operation and an add operation. Duplicate happens all the time. Duplicate happens in every loop iteration, but the add only happens when a 1 bit appears in the sequence of secret bits. And the background, so the chart that you see is what the attacker observes, the latency of the DRAM access that the attacker observes. Of course, it would be, if there would be no activity, it would be just a flat line. But now the victim is going to DRAM and doing some kind of code and data accesses. We don't know what it is, and you might think, well, all I will see is some random noise. But give a security person the idea that there's some kind of activity-dependent signal there, and they will keep pulling the thread and pulling the thread until they can, from that random noise, reconstruct a video of your whole life. So never think it's just random noise too soon. So on the left, you see the raw latency signal of the DRAM accesses that the attacker is doing. Yeah, and it looks like junk, right? It just looks like a bunch of noisy crap. But if you look closer, then you see here is when the victim is doing the duplicate, add duplicate. Sorry, the other way around. Add duplicate, add duplicate, duplicate, add duplicate. So you can see this is part of the code that implies what the secret key looks like. And at first it looks like noise, but then you start to look, hey, wait a second, I see these spikes always at the end of blue, these spikes at the end of blue. Okay, maybe there's a pattern here, and if you smooth the latency signal, so you just take this running average, then suddenly it becomes very clear there's actually a very regular pattern going on. So, let's try and automatically deduce what the real full crypto key is. We apply a machine learning algorithm to the ground truth. So we just run the victim with some instrumentation to give us the ground truth. So we then need to train a machine learning algorithm on what does the pattern look like when I see a doubling. What does the pattern look like when I see an add and an addition? If I can deduce this pattern automatically, I can guess the crypto key. Now at the left, you see the performance of the classifier given the raw signal. And the classifier is just given parts of the signal, and it doesn't know about these boundaries, right? Because in reality, we don't know the boundaries either, because that would already tell us, practically speaking, would already tell us what the adds and duplicates are, because they take different amount of times. But if you just forget about the background shade, and you just imagine that the classifier is given that noisy signal, it's able to reduce blue, green, by this red, the red chart, that's the classifier. And most of the time, it perfectly predicts when you start to see a blue or a green shade. But we have to do a little bit, but it's not completely perfect. So to get the real crypto key, in most cases with public cryptography, you can validate whether a particular guess is right or not. And by looking at the predictions, you can sort of see, well, does this make sense or not? You can try flipping some bits. You can do some brute force to get to the real key. And on the right, you can see when doing real experiments, how many trials did we have to do where after getting the raw classifier guess, by flipping some bits and leaving some bits out and putting some bits in, how many trials did we have to do before we got to the real key? And that is in the very worst case was a little over 1 million, 2 or 4 million trials. But in most cases, you can see here, this is log 2, so this is 2 to the 15 to the 10, very few guesses are really needed. So unfortunately for the victim, hiding from the caches and going to DRAM was a bad move, because not only does the side channel remain, it actually got a little bit easier, because all of the activity in the system to a large degree is confined to the caches, because everyone tries to stay in the cache, right? And if then a victim, if an attacker can use the cache to execute his own code and use the cache to access his own data, and only does uncached accesses to observe the victim's secret accesses, then you get actually a very clear signal of what those secrets are. So the lesson is, it could actually be a good idea. It could actually be, because defense in depth is valuable, and we don't always want to have to be forced to write perfect constant time algorithms. But if you do this, then you have to go further than just CPU microarchitectural resources, and you also have to realize DRAM is a shared resource. And one step beyond this would be make the memory controller help you to give you a dedicated bank. Then you still have probably contention on a DRAM buses and probably some other contentions that the signal will be much weaker. So that could be one step further. So this is probably a good idea, but this is not complete. So if someone tells you, hey, let's just implement a mode where the CPU is in safe mode, don't believe them right away. So that's the message of this talk. Thank you for listening.
Yeah, also for catching up on some time.
No problem.
Are there any questions from the room? Yes.
So when you train for having this disambiguation, do you have the impression that the fact that you use this immunization framework aggravates the situation? How would it be if you didn't have protected the code? Would you have been able to do exactly the same?
No, because I think all the code is so small and and the caches are so big, there would be no DRAM access at all. So that would be this thing would I would have to get this kind of information. You have to go into the cache to see it.
And so I guess was it so that the kind of memory system by default tries to lay out things so that they are in different banks and they're like consecutive code or data, so that the accesses would be faster? Was that right?
So what are you asking?
So like if you have a normal case, like let's say you
Yes.
take like 1 gigabyte of memory somewhere, and there's like some will go to same bank, but then it tries to strike
Yes.
them probably like so that if you have from other bank like next addresses, then it would be faster because then you're not competing with resources but between yourself.
Absolutely, yes.
Yeah.
That can only be the case.
Thanks.
So part of the issue here is that we still have to do this asymmetric crypto in software. We will write our own. So I think what could be a more effective mitigation is to have hardware acceleration. Like AES and I was great. When will we see big num acceleration into CPUs?
Wow. Well, even if I knew, I wouldn't be allowed to tell you. But I believe that for the foreseeable future, in public key crypto, software will continue to play a large role.